Let's compute a few more volumes using the method of cylindrical shells. So displayed on the screen is what we derived in the last video, our two formulas depending on if we are revolving a region about the vertical axis or a horizontal axis. But either way, what we're going to do is we're going to draw our region, we're going to revolve it, and then we're going to determine the radius of a shell of that region, of that solid, and a height of that shell. Once we've done that, we'll set up the integral and we'll integrate and follow it through. So one thing to remember, and it's highlighted from the last video, one thing to remember, I'll highlight it again. Right there is where I'm at on the screen. We'll highlight it again. We're going to slice a rectangle in our region parallel to our axis of revolution, and that's the rectangle we're going to use to determine our radii and our height, depending on if we're going around a vertical axis or a horizontal axis. That's what will determine if we're integrating with respect to x or with respect to y, based on the thickness of our shell. So let's get into some examples, but before we do, let me just project this little image again. Remember that this is what we're doing. We're taking these, they're almost like, you know, the inside, the cardboard piece of a toilet paper roll. We're taking that, we're thinking about just slicing it vertically to open it up and creating this shell that we've opened up, and we can calculate the volume. So that's what we're doing. This is a vertical orientation. Of course, you could take that cylindrical shell and tilt it on its side, and then you'd be looking at a horizontal orientation. All right, let's jump into a couple examples. All right, so this first example, we're going to take a solid. We're going to find the volume of a solid that we form by taking a region that is bounded by the function y equals the cube root of x and the vertical line x equals 8, and revolve it about the x-axis. So one thing to note, when we say we're going to revolve it about the x-axis, that is also giving us a bound right there. That means that we're also going to have a bound of the x-axis. So bounded by the x-axis as well. So we're also going to be bounded by the x-axis there. So we'll keep that in mind as we're graphing this. That is the cube root function. The cube root function is going to look something, let's see if I can get this here. It's going to look something like this. I'm thinking of a couple of points that I can plot to get the good curvature there. There we go. Because at 8, the cube root of 8 is 2, and the cube root of 1 is 1. So we would have that. We've also got the vertical line at x equals 8. You know what? I don't like that vertical line. My hand slipped a little bit. There we go. So there's our vertical line at x. There's x equals 8. Here's the function y equals the cube root of x. Let's just remember that that's also x to the 1/3 if we'd prefer to write it that way. And then we also have, and I'll just kind of, I'll make it solid on the x-axis. Remember, we're also bounded by the x-axis. So the region that we're looking at, I'm going to go ahead and highlight it. The region that we're looking at is this region right here. So we're going to take this region and we want to revolve it about the x-axis. So we want to revolve it about the x-axis. So what would that solid look like? So let's think about that. So a solid that takes that highlighted region and gets revolved around the x-axis. What would that look like? Let's think. So again, this is good practice with three-dimensional drawing and kind of thinking about what do our solids look like. So we're going to have, and again, I'm just going to do, this is my axis of revolution right here. We could dash it out in red. If you've got multiple colors while you're taking notes or while you're doing your homework, that can be helpful. We've got, this is going to be 8, by the way. This is 0. So between 0 and 8, we're taking a region, right? We're swinging around 360 degrees around the x-axis, and we're going to end up with a solid that looks something like this. So it's going to be something like that. That's what our solid, right? So we're taking that region, think about it coming out of the board, coming out of the screen at you, swinging all the way around, tracing out a mirror image down here, and then coming back around and filling in the back. It's actually this, it's completely solid. This guy is completely solid, has no holes or anything like that in it. So we've got a completely solid little, almost like a vase tilted on its side, I guess is one way to think of it. It does come to sort of a point at the end there. It might be hard to sit up. All right, so that's what the solid looks like, and we want to use shells to find this volume. Now, just as a quick note, we could absolutely use the method of discs or washers on this one, and you may, given the choice, if you had the choice, you might choose to go that route. In this section, you will see me do all my examples using the method of shells, but there are also cases where when you get into the homework, it's going to ask you to just make a choice. You pick. And sometimes either way is equally the same, and sometimes one method is better than the other method. Like on the previous example in the last video, we showed an example where it made a lot more sense to use shells. Okay, so just wanted to make that little caveat. I guess I'll make a little note. It would actually be a disk in this case. We could use the method of slicing. That's called the method of slicing. So we could use the method of slicing, and I'll just in parentheses, this would actually be a disk. Okay, but we're not going to in this section. I want to illustrate how to use shells. So we're going to do this example with shells. Okay, so remember when we do shells, what we want to do is we want to take a rectangle in our region that we're revolving that is parallel to our axis of revolution. So over here, I'm going to draw a rectangle and we're going to visualize that getting spun all the way around our axis of revolution to create our cylindrical shell. So over here, here is our little rectangle. It's being spun all the way around. So down here, I'm going to draw it here. This actually should go up just a little bit. There we go. And I'm going to make this thick so you can just kind of see, right, this is creating that shell. And we're going to nest all those shells and create the volume, create the solid, and use those shells to find the volume of that solid. So this is what a shell looks like, where we take a little representative rectangle and we spin it all the way around. So what we need is we need the radius of that shell and we need the height of that shell. So as a reminder, we want to come over here and think about like, what is my thickness? And my thickness is a delta y. The thickness of these shells is a delta y. So our volume, just as a reminder, it was on the previous screen that we started with. But as a reminder, when we're going around a horizontal axis and our rectangles that we spin to create the shells are parallel to that horizontal axis, then our volumes are going to be the integral from c to d of 2 pi times the radius as a function of y times the height as a function of y dy. So we need to come up with a way to represent our radius as a function of y and our height as a function of y. So we're going to do that by looking at, we can either look at the actual shell that we drew. I think it's a little easier because we've labeled the functions over here in the region that we revolved. And so I think it's a little easier if we come over here and we think about what would this radius be and what would this height be as a function of y. And so on that note, if we take a look up here, we have our function here for this bound of the region. We have it written as a function of x. But we could just as easily say, or we could write that as a function of x, because if we were to just a function of y, x as a function of y. So if we were to just cube both sides of that equation, we would find that this is equivalent to x equals y cubed. And that's what we're going to use. So let's say if we had it written y as a function of x, and we just rewrote it x as a function of y, because we know our functions need to be in terms of y. Okay, so coming back here, how do we find the radius? Well, the radius, this height right here, up to the height in our region, up to where we're making the shell cut, that is going to be simply y. It is wherever we're at on the y-axis, whatever y value we're at, minus 0. I'm going to write it as minus 0. Of course, you don't need the minus 0, but that's where the lower, so right, we're taking the upper value minus the lower value, so y minus 0 is just y. And then we're going to do the actual height of the rectangle. So again, now we're kind of flipping our head a little bit, right? We kind of got to look at this as a horizontal slice here. And so we're looking at this and we're saying, okay, well, the function here is actually just x equals 8. It's a constant 8. That value on the right side of this rectangle is always going to be 8. So that's going to be 8 minus what is changing, right, depending on where we take the slice. What is changing is this left side. And so the left side is defined by the function y cubed. So 8 minus y cubed, and that is the height of each of our rectangles that we're spinning. And we know that on the y-axis, we are going from 0, right? We start taking those rectangles and building those shells at 0, and we end up here at 2. There's 1 is somewhere in the middle. So in order to create this solid, we take shells that start at 0, that have a radius of 0 basically, and then we extend out those shells until their radiuses are 2 and nest them to create our solid. So this is going to be, so the volume of this solid is going to be the integral from 0 to 2 of 2 pi times the radius that we found, which is just y, times the height, which is 8 minus y cubed dy. Now I'm going to go ahead and integrate that. I'm going to speed up the video because this is going to be just a little bit of algebra. I'm going to distribute the y, and then I'm going to use my basic rules of integration. So I'm going to, since there's no integration techniques, no specific special integration techniques on this example, I'm just going to go ahead and speed up the video so you can see the work, and then we'll do another example. Our final volume here is 96 pi over 5 units cubed. And that is how we find the volume of a solid using the method of shells. Now we're going to do another example here to finish out this video, but the process is going to be always the same, right? Draw our region, revolve it, draw the solid, draw in a representative shell, and then figure out the radius and the height of that shell in terms of the appropriate variable x or y. Once we've done that, we can set up the integral, and then we just use our integration strategies to calculate the volume. Okay, let's take a look at another example. Let's find the volume of the solid that is formed when we take the region bounded by 2 minus x squared and y equals x, and we revolve it about the line x equals 1. So let's see. This particular graph, this is a parabola and this is a line. So let's get those graphed. It's a parabola. It opens down. Its vertex is up at 2. And this is going to look something like that. I should zoom in a little bit here. And then y equals x. Would be this line. So here's y equals x. Here's y equals 2 minus x squared. And let's figure out where those, I'm going to get rid of that 3 on the y-axis. Looks like I was raising x to the 23rd, but it's actually just x squared. Let's go ahead and figure out where those intersection points are. I actually think I graphed it fairly decently, but that's our region and we're going to revolve it. But let's figure out those intersection points just as a little review. Intersection points. So remember, we find intersection points by simply setting our two curves equal to each other. So 2 minus x squared equals x. And I will say you want to be a little bit cautious of just assuming that you can guess your intersection points off of a graph. I think on this one, if we had done a really good job graphing it, that might have been the case. Sorry, I'm trying to talk and work at the same time. I'm going to move all those terms to one side, and then I'm going to go ahead and factor x plus 2, x minus 1 equals 0. So my intersection points here are going to be when x is negative 2 and when x is positive 1. So I did do a pretty decent job. They're pretty close. I'll make the dots big enough so they're exactly on. And then that would give us, if I plug negative 2 back in, x equals y. So this will be at negative 2, and at 1, 1. So 1, 1, and negative 2, negative 2 for my intersection points. Just want to caution you though, right, this is how we find our intersection points always. This was a fairly simple algebra equation, just a quadratic to solve that actually factored, but that's how we always find our intersection points. And so unless they're given, let's make sure that we double check and we get the right intersection points. Okay, so we're going to revolve this. Let's go ahead and draw in our axis of revolution. So our axis of revolution is, and it's not the x or the y axis, it's x equals 1. So x equals 1 is this line right here. So x equals 1 is my axis of revolution, and that's where I'm going to spin this graph. I'm going to spin my graph around that. So x equals 1 gives us, it's going to be kind of an interesting little solid. So let's think about what that solid looks like. That is a vertical line, and my solid is going to look something. Let's go ahead and get this guy graphed again. Now, since this is going around x equals 1, I'm going to go ahead, I'm going to grab my eraser real quick and change that. We're going to have to dash out some of this as well. That's going to be behind, inside the solid. And then we've got our axis of revolution. I'm going to draw it as a solid red line just so that it's easy to see. X equals 1 is my axis of revolution. Axis of revolution. And let's get this guy dashed out on the other side. All right, so we've got this solid. We took this region and then we revolved it all the way around. So this is kind of an interesting little solid that we've created here. It almost looks like an upside down bowl in a way, but it does have that kind of opening on the top and then also an opening on the bottom, but it comes to a point here where we can see them here. So we are going to draw a representative shell, because remember what we're going to do is we're going to take a rectangle parallel to our axis of revolution. So here's our rectangle parallel to our axis of revolution, and we're going to revolve it around. So I'm going to draw the same sort of rectangle over here and draw a representative shell. We're going to take that, and that's going to create a cylindrical shell when we revolve it around that line, x equals 1, that vertical line. It's going to create a shell. I'm going to give this kind of just some thickness coming around, some, some thickness over here, and some thickness down here as that goes around, creating that shell. Okay. And so we end up with a shell that looks something like that. And now we need to figure out what is the radius of that shell and what is the height of that shell. And we need it to be with respect to, we could do this on either drawing, but I'm going to come over here to our region. This is going to be a delta x, a thickness of x. So we need both our radius to be a function of x and our height to be a function of x, because our volume formula when we're doing shells is going to be the integral from a to b of 2 pi times the radius of the shell, but we need that radius to be in terms of x because the thickness is in terms of x. So I'm going to write that as r of x times h of x, the height in terms of x, dx, because the thickness of our shells is a delta x. So let's go ahead and get in here and think about that relative to the region. I'm going to zoom in a little bit so that we can really look at this region. This is going to be the radius of the shell, this length from here to here, so that's r, and this is going to be the height of the shell. So wherever we're at, whatever x value we're at right there, when we take that little slice parallel to that axis of revolution, we take that little rectangular slice and we spin it around that axis of revolution, wherever we're at on the x-axis right there, to find that radius, we actually have to start at 1 and subtract wherever we're at on the x-axis. So the radius becomes 1 minus x from the axis of revolution, which is at a fixed value of 1, minus where we make that, that rectangular slice that we're going to spin around. Okay, so 1 minus x, and then the height is going to be the output value for that x here at the top function minus the output value at the bottom function. So we could think of this as our top function and our bottom function. So it's going to be 2 minus x squared minus x. And I will write it that way just so we can see it's the top function minus the bottom function. Just simplified, I guess I could write that as negative x squared minus x plus 2. So that is how we calculate our radius and our height. And now we go back into our integral and we're going to integrate. We are going to start creating those shells at -2, and we're going to get all the way to 1, nesting all those shells. So our bounds are from -2 to 1. So this is the integral from -2 to 1 of 2 pi times 1 minus x times negative x squared minus x plus 2 dx. And so that's our integral, and now we just have to calculate that volume. So again, like in the last example, I'm going to go ahead and calculate that volume. I'm going to speed up the video here so you can just see the calculations in quicker time, and we will find our volume by integrating this. And we'll go ahead and do that because there's just, again, just some algebra to do here to expand out that product, and then it's some basic integration. And there we have our volume, 27 pi over 2 units cubed of volume for this fun little solid. See if we can get it all on the page. For this fun little solid that we had by taking that parabola in that line and revolving it around a vertical axis that wasn't actually the y-axis. So we can revolve around vertical and horizontal axes that are not the x or the y-axis, and we just have to be careful when we're setting up our radius and our height that we take that shift into account.